Yes, okay. We have now the third talk from Carlos. Carlos, thank you once more, and please, you can start.
Okay, thank you. So thank you. Hope everybody had a good coffee break. I'm going to present the last lecture of this series on supersolids and ultra-cold atoms and dipolar molecules. And what I would like to discuss next, I just remind you what the topics of the lectures were. The first one was about dipolar boson supersolids in the continuum, or traps or box traps. So there's no lattice here. Then I moved on to analyze dipolar bosons in supersolids and optical lattices just a minute ago, an hour ago. And now I'm going to be focusing again on supersolids as emerging from superfluids, but in a different system, in which you have now spin orbit coupled systems or bosons. So you don't really need to have long range interactions to stabilize supersolid phases, but you can have supersolids arising in spin orbit coupled bosons without the long range interactions, which are discussed in the two first lectures. So I'm going to go now to lecture 3 and talk about supersolids in spin orbit coupled bosons. So the outline of lecture 3 will be basically a short introduction on artificial spin orbit coupling, what it is and why it's interesting, at least to me. Then I'll go on and review spin orbit coupled bosons in the continuum. That's basically saying harmonic traps or box traps. And then move on to supersolid spin orbit coupled bosons in optical lattices. So go to the same system, but now look at the effects optical lattices have. Then I'll show that one of the interesting things about optical lattices is that you have what we call a supersolid devil's staircase that arises in the system. And I will conclude, telling you more or less what I have told you. So as I do in every lecture, I'll come up with the conclusions first to give you an idea of where we're going. Just get some water. And conclusion in words again, our working definition is supersolid is that a system that exhibits superfluid and crystalline order. And we're going to be looking at the case where this crystalline order arises from a superfluid. In the case of spin orbit coupled bosons, we're also going to focus more on two-dimensional optical lattices, but they can exist also in 3D, which is a bit more difficult with dipolar systems. So supersolid phases spin orbit coupled bosons can exist in 1D, 2D, and 3D. Depending on the parameters of the theory and the spin orbit coupling, the Zeeman field, Rabi fields, the superfluid phases emerge also out of the superfluid phases and away from multi-insulating. So I'm going to show what the phase diagram looks like when you have local interactions and spin orbit coupling for the bosons. And then I also discuss the case in which, like in the dipolar system, you can have isotropic and anisotropic supersolid phases, which will arise in this case depending on the direction of the spin orbit coupling with respect to principal axis of the lattices. So this is analogous to what would happen with the application of an electric field or a magnetic field. So depending on this angle where the spin orbit coupling is respect to the optical lattice principal axis, you can have different phases, as I discussed just an hour ago in the case of dipolar systems. And lastly, I will mention about the existence of a devil's staircase, which is a series of supersolid phases that arise. It forms a dense set due to the commensurability of the fundamental period of the supersolid modulation and the underlying periods of the optical lattice. And these phases are stabilized by the interactions, so they are very robust, and it would be a very nice hallmark of the observation of the supersolid phases to see this devil's staircase. Okay, so then in pictures, what I would show is that you have seen before when you had bosons with just no internal degrees of freedom, we have the standard or the traditional Fisher phase diagram of the chemical potential along the vertical axis here, and T over U along the right axis. And you have these Mott lobes indicating the insulating phases. Now in the system, you have bosons with 2 internal degrees of freedom, so a pseudo spin 1/2 boson, in which you apply then spin orbit coupling and Rabi field, omega. And what you can see is that without this Rabi field, the superfluid phase will be expanding the entire region outside the Mott lobes. But when you have spin orbit coupling phase in green here, called stripe phase supersolids, the rise, and we show this first for the case of spin-dependent spin orbit coupling along the x direction. And you see the emergence of several phases. Before, you had only Mott insulating phases in gray and a superfluid phase. Now, when you add spin orbit coupling, you have supersolid stripes, superfluids, Mott insulator, and a regional phase separation. And what I will show is that these 4 types of phases, they have very distinct momentum distribution that can be detected in time of flight. For the Mott insulating and the superfluid cases, I mean, I already discussed what those things were in the nice experiment by Emmanuel Bloch. The difference here is that the spins are not equivalent anymore. So the Mott insulating phase has this blob around k equals to 0, very broad. The superfluid phase would have this very sharp feature at k equals to 0. And then the additional phase that could be seen in time of flight also be this supersolid stripe phase, which have several peaks associated with the periodicity of the system. We have multiple components, and these multiple components arise due to unclop processes. And of course, you can have a phase-separated system, which you can peak Bose-Einstein condensation and in a system of positive Q or negative Q, and that would correspond to a phase-separated state, in which you have everybody on positive Q minimum or everybody in the negative Q minimum. It's a phase-separated state. So momentum distribution in time of flight would be able to see a marked difference between the stripe supersolid, the Mott insulator, and the superfluid, as well as the phase-separated state. And if I include the idea that inducing the spin-orbit coupling, and I have a tilt angle where the spin-orbit coupling is changed, not only parallel to one axis, let's say this will be the x direction, and this will be the y direction of a, say, 2-dimensional lattice. What we see in this figure here is regions. These are the regions where you have supersolid phases, depending on the darker orange color region of supersolid phases. And the cool thing about it is actually that this supersolid phases, if the tilt angle, the angle is about 45 degrees in which the momentum transfer occurs, then the period of the supersolid phase along the x direction, the y direction is exactly the same. So you have a period 2 system, which will be like a checkerboard. On the other hand, if you change the angle in which the spin orbit coupling momentum transfer occurs between this range, you can see that you can have periods which are different from isotropic from 2A on both directions. You can have a period in which the supersolid phase has a period 3/2 of the lattice period, or have a period 1/3 3 times of the lattice period, right, along the x and the y direction. So as you tilt the angle, you're going to be also tilting the symmetry associated with the supersolid phases that have different periods than the lattice. Period 2, then you can have periods 3 on one direction, periods 3/2 in the other direction, depending on the angle. So this is similar to what you expect or what you see in the case of an electric or magnetic field for dipolar bosons. So any other angle, the periods will be different, provided that you are in the region of stability. This tells you where the supersolid phases are stable. Here, this area in which are showing gray, or the endpoints showing by the triangles, show the phase in which you have a single momentum. So this means you have a structure which has 2 minima, and everybody is in a single minima. So those phases will be like a sort of a phase-separated regime. But as long as the momentum transfer is here with some Rabi frequencies, for fixed interactions, this is approximately the case for rubidium, 87, you have the supersolid phases, and you have this cascade of phases with different periods, and that's called a devil's staircase. The reason why it's called a devil's staircase is because the set of commensurate phases is dense, right? So this Q vector, which tells you the periodicity along the x direction and periodicity along the y direction of the supersolid phase, has an infinite number of periods which are commensurate with the underlying lattice, and that's called a devil's staircase. Okay, so let me, since I'm talking not anymore about dipolar bosons, I'll be talking about spin-orbit coupling. I will begin by introducing to you what artificial spin-orbit coupling is, what spin-orbit coupling is in the context of cold atoms, the experiments that have been done so far. So this idea, we discussed a little bit that in light of a beautiful experiment that was done by Jan Spielmann, exactly in the same Nature magazine. And I just want to point out where they generated artificial spin-orbit coupling. I just want to point out that the artificial spin-orbit coupling that's created in cold atoms is completely different from spin-orbit coupling, which you can view as relativistic corrections in standard atoms or in standard solids. And as we know, I mean, the idea is simple to see. By just changing reference frames, you can see that if in an atom, if the electron is orbiting around the nucleus, you have an orbital motion, the electron has a spin. From the point of view of the proton, that's what you see. From the point of view of the electron has a spin and sees the proton going around, and therefore the magnetic field, right, created by the proton couples with the spin, and so the spin-orbit coupling arises from this sort of point of view, and of course is a relativistic effect. You can obtain that directly from the Dirac equation. And in a solid, you can do the same argument. The electron is moving around the solid, the ions are here. From the point of view of the electron has a spin, the ions are moving around, they create a magnetic field, and the spin-orbit coupling is precisely this. So in spin-orbit cold atoms, the situation is different. What you want is you want to create artificially a coupling between the internal degrees of freedom of the spin of an atom and its center of mass momentum. So the question is, how can you do that? And that it was achieved experimentally first in the group of Jan Spielmann, although there were some ideas already from Jean Dalibard on how to do those experiments. But Spielmann was the first to implement that. And it's to think about how can you simulate or create artificial spin-orbit coupling in bosons or fermions for that matter. And the idea is generally simple. Is to create a setup in which you have atoms which are trapped in a box trap, in a harmonic trap, or a lattice, and shine in Raman beams, which are opposite in direction, in such a way to cause internal transitions, or 2 photon transitions, between the internal states of the atom. And how that is achieved? Well, the idea then is that you imagine that you have 2 internal states, which are red and blue, you can call spin up and spin down, pseudo spin up, spin down states. And you can shine these two Raman beams and cause transitions between the lower state to the upper state and down, and vice versa, the direct and the reverse Raman transition, right? Which in this process transfer some momentum to the states which are opposite in direction. So the spin up states through a Raman process can get a kick, let's say, to the right, due to this two photon absorption, two photon process, one absorption and one stimulated emission. And the other spin state, or the other internal state, can absorb the photon and then by stimulated emission emit another photon and get a momentum kick in the opposite direction. So the total momentum transfer here for a spin up and spin down component is going to be in opposite directions, provided that these beams are opposite each other. So omega square, omega is the Rabi frequency, which is proportional to the field square, which is just tell you that your coupling states number 1 and 2, or states up and down. And the detuning corresponds to the offset of the Raman laser frequency with respect to the transitions, resonant transitions of the two levels. So that's a very simple way to see that. And by looking at this expression, this is a Hamiltonian for a single atom, you can already see that this system here, which absorbs a photon and emits another photon, and the same thing here, and absorb a photon, emit a photon, but in opposite directions, you can see immediately that the kinetic energy of those systems depend on the spin state. If the spin state is plus, then you have a momentum transfer which is plus kT. If the spin state is down, you have a momentum transfer which is minus kT. So the kinetic energy is now dependent on spin. You can see there's a spin orbit coupling immediately if you just observe that. So in order to see this in a more condensed matter way, the way that people like to see, is that you can make a simple rotation, SU2 rotation to a new basis. And that new spin basis is just to say that instead of doing the quantization axis along some arbitrary z direction, which you label the spin states, you can make SU2 transformation such a way that the old SX, old X direction becomes Z, old Z becomes Y, old Y becomes X. And by doing that, you rotate the direction of the quantization axis. And you can rewrite now this Hamiltonian in a way which is more familiar to condensed matter physics, which is very simple. You have now a kinetic energy of the system, which is shifted by the momentum transfer energy. Omega, which was before along the X direction right here, gets transformed into the Z direction. So it becomes a Rabi field becomes a standard Zeeman field along the Z axis, the new Z axis. And the detuning and the momentum transfer coming from the expansion of the linear term in KT. If you expand that, you have K squared plus KT dot K times KT squared. So we have a linear term which couples this momentum transfer to the momentum of the system. And you can see clearly that this thing here becomes effectively a magnetic field along the Y direction. You can see that because of the I polymeter. So this is a spin orbit coupled system because this field here, effective field, depends on momentum Kx. Right? So it depends on momentum as well. So that's the spin orbit coupling. You're coupling the spin degrees of freedom with the momentum, in this case, along the X direction, which is the direction of the Raman beams. So that's what experimentally was achieved through this work with Jan Spielman. So the KTM times Kx is the spin orbit coupling. The delta here is the detuning. The Rabi coupling is essentially the Zeeman field. So the delta is a Zeeman field along the Y direction. The omega is a Zeeman field along the new Z direction. And this part here is a magnetic field, which is dependent on Kx, which is then a spin orbit field along the Y direction. So this is created. So what did they do with that? So let me tell you a little bit what the experiments were for spin orbit coupled bosons and what did they find. So now you can write down that Hamiltonian matrix into this representation, which is a kinetic energy with the shifted kT square, and some effective field that depends on K, because you have spin orbit, that depends on the spin components as well. So this Hamiltonian that we saw, there was a 2x2 matrix. We could write this Hamiltonian as some kinetic energy plus some field, and this H parallel is along HZ direction, so it's going to be H parallel is going to be the Zeeman field, and H perpendicular is going to be along the X and Y direction, which I can find here. So it's a 2x2 matrix, which is K dependent. We know how to diagonalize that. We can rewrite the whole thing, of course, in terms of the Pauli matrices, with the field along the X direction, along the Y direction, along the Z direction. This is a momentum space two-level system. We know how to diagonalize. So this is just a particle with the momentum K, subject to an external effective magnetic field, which is momentum dependent. It has components Hx, Hy, and Hz. So you diagonalize that, of course, and you find that the new eigenstates, this is the new pseudo-spin up and down, has the kinetic energy that they had before, plus or minus the magnitude of the effective magnetic field, which is a square root of the square of the components, the sum of the square of the components. So H effective is going to be Hx squared plus Hy squared plus Hz squared, square root of that. So that's a simple problem, or two-level system problem. And depending on the nature of the spin orbit field, which is this field here this is corresponding to the spin orbit component, the HSS prime, you can have something interesting, which is in quantum metaphysics is known the Rashba spin orbit coupling, in which the field, the spin orbit field that you have, depends on KY and KX and has a chiral symmetry. So if you look at what the direction of the spin orbit field is in K space, it's circulating around. So it has some chirality associated with that. You can see that from the KY plus IKY. That's called the Rashba spin orbit coupling field. And what it does to those dispersion that we talked about, you can see that dispersion has two components. So if this field that we wrote is of the Rashba type, which is this one here, which has a component along the X direction, which is VRKY, and a component along the Y direction, which is VRKX, it creates two bands. So there's a pseudo-spin up and pseudo-spin down bands. And these two bands have the structure like this. There's one band that looks like that, with a minimum, a Mexican hat type. The second band is like this. And there's a diabolical point. There's a point in which they merge right there. So this is the spin orbit coupling that you can have, let's say, in condensed metaphysics. Now the ones, now there has been created now in cold atoms also using more complicated setups. But the simple setup that using the Raman beams that I just described to you is actually of this form. It's called the equal Rashba-Dresselhaus term, in which you have a spin orbit coupling with momentum transfer only along the X direction. So the effective field, magnetic field, which is dependent on K, that is shown here. So depending on the value of Kx, these field lines are showing pointing up along the positive Y direction. Of Kx is negative, is pointing along the negative Ky direction. And it can be shown as being the sum of these two terms, which are called the Rashba term and the Dresselhaus term in the connection to condensed metaphysics. But this is the term in which you create a momentum transfer along the X direction. And that produces, again, two bands, which are like this. And they're different from the Rashba in the case that if you have no Zeeman field, those bands, of course, there has no minima. They're just shifted from each other. But if there's a small Zeeman field, Rabi field, there's a split, and those two bands are separated out from each other. But they are clearly anisotropic. And the reason why they're anisotropic is that you created a momentum kick or shift in momentum centers to the right or to the left. So this situation is the experimental situation that I'm going to be talking about. So the way you want to see this is if the fields are 0, Hz is equal to 0, and you give a momentum kick along the X direction, the bands that you started with, something like that, they get shifted to the right or to the left, by that momentum kick. And the spectrum of those systems are exactly equal to the shifted bands by the amount of momentum transfer to the right or to the left. On the other hand, if you apply now a Zeeman field or a Rabi field, these two bands that were shifted to the right and to the left with respect to the original parabolic band, they split. And if this Zeeman field along the z-axis, the omega, is small enough, you can see there's a double minimum structure that arises in the lower band. If this omega field or HZ field becomes very large, this minimum obviously disappears, and you can have a single minimum K equals 0. So in the case this is not too big, you have double minima. If you're talking about bosons, you can have both condensation on the right and on the left minima, and then you can have presumably like interference effects between those two. So if you now have some detuning, which is this HZ, the real part of you can shift one component and detune one of the components to the right or to the left. And this shift is coming out from the detuning term along the y direction, which is the delta over 2. So this is the essentially delta over 2, the detuning. This is the spin orbit coupling field that shifts back and forth. And this is the Rabi field divided by 2. So the Rabi field resplits, the detuning creates an asymmetry, and the spin orbit coupling creates shifts to the right and to the left. It was by doing this that Jan Spielman at NIST and the JQI studied the rubidium 87, loaded those systems, and analyzed a phase diagram of the detuning, which controls the asymmetry between those bands, the lower bands, and the Raman coupling, omega, right, or the Zeeman field along the z-axis, and obtain a phase diagram in which if omega is sufficiently large, then the lower band has a single minimum, and therefore you have some Bose-Einstein condensation system that occurs for large omega. On the other hand, as omega, as the Raman coupling gets smaller, you enter into a regime in which right here you have a double minimum, but the system gets confused, doesn't know if it's going to stay on the minimum to the right, only the minimum to the left. So when delta goes to 0, these two minima become degenerate, and the system does not know precisely in which minimum it's going to stay. So there's a region here at 0 detuning, which the system is phase separated, which is zoomed in here. And then if omega gets smaller and smaller, the system can mix. So you have two minima, which are degenerate, and you can have a Bose-Einstein condensates on the positive minima and the negative minima. Negative momentum minima and positive momentum minima, and you have a mixed. So Jan Spielman was able to show that indeed, in particular, away from that, you're going to have these regions where the system has a single minima, which he didn't find it was so interesting. The most interesting region was in which the case in which you find omega sufficiently small, and there are 3 points here along this line, which we just zoom in from here. Now we zoom in into this mixed area, and if you zoom into that area, you can see that when the Raman coupling is sufficiently large, you have phase separation between the up and down components, red and blue. As you keep decreasing the Raman coupling, the Zeeman field a little bit lower, it's still phase separated state, and then eventually all those guys are mixed. So into this mixed phase. So the spin up and down components are all mixed in. So there's a condensation in the two minima. So that's a mixed thing. Now, the interesting thing about this is just following these results in 2011, right here in this mixed phase, there was a nice paper by Jason Ho and Qishong Zhang, in which they said, well, I want to take a closer look at what this phase is. So let me take a look at this minima. And what they found out is, of course, that this mixed state is not completely uniform, has some kind of oscillations. And the reason for that is not very hard to see, is that if you have a Bose-Einstein condensate with finite momentum k, and plus k0 and minus k0, you can think of them as creating some interference pattern, which can be stabilized by interactions. provided that interactions are not too strong, to kick those things out and eliminate these minima, these two minima. So he proposed that this phase is, if you could have a better resolution instead of just this blob here, you know it's mixed, but you don't know exactly what it is. If you had a better resolution, you could be able to see this pattern, which will be a function of 2k0, this difference in momenta because of the interference patterns. If the interaction was not too strong. If the interactions were too strong, then this will be just some kind of superfluid, it wouldn't be there. So, and this was, 2011, about 6-7 months after Spielman experiment. They decided to take a look at that region. Then in 2013, another 2 years later, there was an interesting paper by Levitaevsky, Sandro Cingari in their group at Trento, in which they decided to take even a closer look at what this phase that was proposed by Ho and Zhang earlier is this modulation that you have there, this stripe thing. What kind of stuff is that? And they were able to show that these objects here are actually supersolids. Okay? And the way to do it, I mentioned to you last time, looking at the structure factor is a better indicator to see this. And they compute both structure factors of density and spin. And they show that the structure factor diverges at the period precisely that you have matching these two minima. And this divergence is telling you that the system then has a well-defined peak. So it's a solid from the Bragg's spectroscopy point of view. And therefore, because it has also superfluid properties, it's going to be a supersolid. So crystalline order and superfluidity at the same time give you supersolidity. And another 4 years later, now 4 years, there was an experiment by Garrel's group with all these authors that appeared in Nature in 2017, which they again sort of reproduce Jan Spielman's experiment, but go deeper into this region where this supposed stripe phase to actually try to see if they can experimentally recognize that this system really is a supersolid. So they're set up to do some Bragg scattering experiment to see if they can actually analyze according to the discussion that Levitaevsky and Cingari had proposed. So they did this experiment, and I noticed in the paper that they labeled this incorrectly. This is not spin-orbit coupling strength. It should be really, I think, the Raman coupling. But in any case, as it is in Spielman's paper, the tuning versus Raman coupling, and they probe this region inside the stripe phase to see. So they have done some experiments, and the idea then of the experiment is that, imagine you try to get a Bragg signal out of that, and if you have bosons and you have a double minimum like this, you can have interference patterns between the Bose-Einstein condensate in the right well and the left well, and if there is, and then the spin-orbit coupling, those two spin states are spin-orbit coupled, and then if there is such a state, then there should be some kind of periodic modulation along the direction of the coupling. The moment the coupling is along this direction, and if they do a Bragg scattering of the system, they should see this modulation, and they claim to see that into some Bragg peak, which rises above an experiment which includes both Bragg and Rayleigh. So they claim, I look at this, I see there's something here, but the claim is that that they see a Bragg peak, and therefore they confirm that this phase is a supersolid phase. So the question is now, okay, apparently it has been a succession of one experiment, two theory papers, another experiment to show that the supersolid phases seem to exist in spin-orbit coupled systems in the continuum. So the question is, can you do or see something like that in the solid and in an optical lattice, and what will be the difference between that and what has been already observed? So I want to then move on to supersolids in spin-orbit coupled in optical lattices. Right now, there are no experiments. There are some experiments being attempted, I think, soon, And the idea here was proposed in this paper, 2017. Jan Spielman is a co-author in this paper. We're wondering if this would be possible. And so we analyzed theoretically this problem of spin-orbit supersolidity in spin-orbit coupled bosons and optical lattices. And the idea here then is that instead of having a continuum system or a box potential, we have bosons which are already loaded in an optical lattice, and you can do a similar setup in which you apply two Raman beams in the opposite directions. And of course, you can give a momentum kick to an atom which is sitting on one side, either to the right or to the left. And depending on doing that, you can give a spin-dependent momentum kick in the same way that you do for atoms in the box potential or in the continuum or in a harmonic trap. So the setup is pretty similar, but the first example that I'm going to tell you about is the example in which the Raman beams align precisely with one direction of the crystal lattice. But if you tilt it, there's some interesting things that happen, which I'll talk in a few minutes. So you put the same setup, and you have momentum transfer due to the two-photon process. A is the lattice spacing that sometimes I'm going to set equal to 1, sometimes I'm going to keep it. So the idea then now is that if you have a lattice, then the spin-orbit coupling that you have essentially is going to be giving you a phase shift, a momentum shift, a momentum kick that appears between the hoppings on site I and J. That's the momentum translation operator, if you wish, between sites R and J. And that's a spin dependent. That's why you have an S here. Depending on the internal state, the momentum kick is to the right or to the left. And H here corresponds to the fields that I described to you, which now are this thing here is going to be also like a field, but I already incorporated into the momentum kick. And you have a field here that involves the tuning or the Raman and the chemical potential. So as done in the continuum, you can write down this independent particle Hamiltonian in terms of a 2x2 matrix, because you have two internal states. We can have a three-dimensional lattice, for example, or two-dimensional. We can have this last one dropped out. A here is set equals to 1, the lattice size. Omega corresponds again to the Raman coupling, the Rabi field. Delta is the detuning between the levels. And the spin-orbit coupling now here manifests itself by the shift in momentum, and that's going to be along the x direction by some spin-dependent term, S KT. So essentially the same type of Hamiltonian, except that you have now periodicity in the lattice, and you have the dispersion being cosinusoidal instead of being parabolic. So you can again diagonalize this 2x2 system is the same way as it did before. So you're going to have two branches, a positive branch and a negative branch associated with that. And with the kinetic energy, which is going to be spin dependent, which means that the spin-orbit coupling coming out from the term controlled by KT. So if you do, you can do the same thing. So if you have zero detuning and you have in some spin-orbit coupling, you can shift the bands to the right and to the left. The Rabi frequency is going to open up a gap, and you have a minimum in the case of omega being small, which is going to have the two states present. That's going to be some kind of stripe, interference of this Bose-Einstein condensates. If omega is sufficiently large, this double minimum disappears. You have a single minimum at k equals to 0. If you have some detuning, you can bias one minimum against the other. So you're going to have a single Bose-Einstein condensate on the left. So superfluid minus, it's going to be the Bose-Einstein condensate to the left. An S superfluid phase plus is going to be Bose-Einstein condensation to the right. A superfluid at 0K is going to be the purple guys. And a stripe phase will be some kind of interference between those two guys, which is stabilized by interactions. So now the system has some local interaction, which depends on the spin states. We're looking at the case, for example, for rubidium, which has equal spin interactions and opposite spin interactions, represented by U up, up, U down, down, and U up, down. And we can look at the phase diagram that you get in those systems. First, at the case where the interactions are very weak. And we can see that when interactions are very weak, we recover precisely the phase diagram that Jan Spielmann obtained experimentally, which means when interactions are very weak, the densities here also going to be low, and you can approximate your bands parabolically, and you have essentially the same phase diagram of parabolic bands, which we discussed before. Now, the interesting thing here, though, is that if even in the low, in this regime, because you have really periodicity, then for a fixed omega, in such a way that you have two minima, you can have several stripe phases. Not only one stripe phase, but several. In the continuum, you can have only one period. In here, you have many, many periods. So the periodicity can be that which is twice of the underlying lattice, which corresponds to this value of 1/2 here, can be 3 times corresponding to this value here, could be 1.5 times the period of the lattice. So what interactions do, and that's essentially due to Umklapp processes, is that instead of having a single period, right, you have the action of combination of spin-orbit coupling and the Umklapp processes to stabilize the possibility of many, many stripe phases, which are supersolid. And the periods can be changing depending on the values of the momentum transfer and depending on the values of the Rabi frequency. So the most interesting case for us, again, is the case of delta equals to 0, because it's exactly where the stripe phases occur, or delta is small. Right? Otherwise, you get out of this supersolid phases and go to the single minima, which for us is not so interesting. So this type of supersolid phases, of course, there's the period 2, and we show them here, what the supersolid phase look in period 2. And I show here also not only the density profile represented by the dots, which are essentially the same, but also the wave function, showing that there are some phases or some currents associated with the spin-orbit coupling. So, and here you can see a period 3 case in which the density indicated by the dots repeat themselves every 3 lattice sites, 1, 2, 3, 1, 2, 3. In this case, the period 4 supersolid phase. I only repeat along the x direction. Those things repeat each other along the y direction, so I don't crowd the figure. And along the x direction, you have a stripe again, right? So it repeats 1, 2, 3, 4, 1, 2, 3, 4, repeats itself. These are the density profiles, and these are the indications of the currents associated with this. So there's some chirality associated with that. So in case of bosons in optical lattices, then the phase diagram that we have for those systems is not as simple as that, because this is the phase diagram without spin-orbit coupling. When we add spin-orbit coupling, we have things which are very different as before. So here is essentially the case in which you have mod insulating phases or the superfluid phases. When you turn on omega, the Rabi field, which creates this double minimum, you see pretty much supersolids everywhere. And that's the situation because you have a double minimum. So you have Bose-Einstein condensation on 2 minima. They have some quantum interference, and they produce some striped supersolid. So immediately for very small omega, right, the phase diagram is very, very different already from the phase diagram that you get when you have no internal states, or you have internal states but no spin-orbit coupling, no Zeeman fields. And of course, as omega gets stronger and stronger, the system goes into a single minimum mode. So this means the superfluid region starts to expand, and the supersolid region or striped region start to disappear as omega gets larger. And eventually, when omega is very large, the stripe phases go away. So the stripe phases appear arbitrarily small omega, and then disappear if omega exceeds some critical value. And so what we show here now is just that you can have several phases, though. You can have stripe phases, you have insulating phases, you have superfluid phases at 0 center of mass, and you have phase-separated states. And so here we show an example. If you tune the lattice depth, or U over T, and you fix the frequency omega, you can visit those 4 phases with some given parameters. And so we can plot this thing here for changing the lattice depth, or U over T, for fixed omega Rabi frequency. And you can see that you can have multi-insulating phases, superfluid phases with one component, stripe phases, and phase-separated states. And of course, to identify these phases, you want to do some experiment. So if you're here, and you can tune the lattice depth, right? So in this case, when you can tune the lattice depth as you change U over T, and then you can visit a phase-separated state where there's a minimum either on the positive side or on the negative side of the dispersion. There's a superfluid phase which happens at k equals to 0 if you have a single minimum. There's a multi-insulator phase which happens when U is sufficiently large, which gives you this momentum distribution, as similar to the Bloch example without spins. So there's a blurred thing. And there's a stripe phase which have a series of characteristic minima at commensurate wave vectors, which are showed up here. So you can see that every one of those states can be characterized, for instance, by a measurement of, they can be distinguished from each other by a measurement of the momentum distribution. So now that brings us to the last thing, which is going to be how do you have now supersolid phases are well established if you apply the Raman fields opposite in direction along the x direction of the lattice. How do you get this supersolid Devil's staircases? So this is an unpublished work. It's been submitted recently, about a month ago. And it investigates the supersolid Devil's staircases in those systems. And the idea now is very similar to what we had before, except, of course, that we want to explore an additional degree of freedom, which is tilting the axis in which these Raman beams are sent with respect to the lattice principal axis. So now momentum transfer is going to form an angle. Momentum transfer between for spin up or down states is going to be kT, but it's going to form an angle theta with respect to the direction of the lattice in the xy plane, for instance, or the xz plane. Okay, or xy plane in this case. Z is out of the plane. So in doing so, then this means that you have the dispersion that you had before, which had a momentum transfer along the x direction alone, now has a momentum transfer along the x direction, and a momentum transfer along the y direction. So the bands that you can obtain, again, by diagonalizers 2 by 2 are now tilted by this angle theta. So the minima occur at some different values of k, x and ky. So it's a point, kx and ky, another point in kx and ky. And for the lower band, it's no longer along the x direction. Well, that, of course, allows you then to have commensurability not only along the x direction, but also along the y direction, because those minima have now waves that can interfere both along the x and the y direction. So when you include then, of course, the interactions, which are essential to stabilize these phases, without them, there's no supersolidity, there's no superfluidity even. You have interactions are required. You can look at solutions of the system in terms of Fourier components, where the order parameter in k space, and here represents a momentum, can have momentum q labeled by a fundamental q and some shift, and this is some momentum index that due to the higher Fourier components that you can have, so you can make a complete Fourier component of the system. Compute the energy of those guys under this assumption that the system has a Bose-Einstein condensate locally, right, which is not uniform, so it depends from site to site, and include all the Fourier components of the system and minimize the energy of the ground state with respect to all these Fourier components. So in this case, when you include the interactions like that, these interactions have a form which is relatively simple. We have some term here which involves the interactions which is spin dependent, and a set of phases for different momentum components and the same spin, which will minimize this energy if a relationship between the phases is such that if these coefficients are positive, this phase is going to be essentially a multiple of pi, or is this phase, if this thing is negative, I'm sorry, if this phase is positive, this phases here would have be a multiple of 2 pi, and if this thing is positive, this will be, if this thing is negative, it will be a multiple of 2 pi. If these coefficients are negative, it will be a multiple of pi in order to lower the energy. And in doing so, these phases get established a very relation between them, which is similar to a Josephson effect, let's say in momentum space, in such a way that the modulation of the Fourier components become commensurate with the underlying reciprocal lattice vectors. This energy is minimized. So this means that the modulation of this lattice has to be a multiple integer, or has a period which is commensurate to the periods g1 along the x direction and g2 along the y direction. And that means that phases that can exist are phases that have, let's say in this case, a period 2 along the x direction and a period 4 along the y direction, right, is represented by some angle that you apply. And depending on the angle, the periods along the x direction, along the y direction can be different. So in this case, I just show here a representation, just focus on the blue line, that shows as you change the momentum transfer, the period of this system along the x direction, for instance, can change, as I showed you before, from period 2 to period 3 to period 4 to period 5 and so on. And there's a cascade of periods going on either up or down, and that's called the devil's staircase. And just to show to you that the tilting of the angle, what it produces is, of course, that depending on the angle that you put, then you can make the periods along the x and the y direction to be different. In this case, when you're at 45 degree and close to 45 degree, the periods along the x and y direction will be the same. So 2a period is going to be some checkerboard kind of period. On the other hand, if you go to, let's say, 66 degrees, the periods between x and y could be different. Let's say you can have a period 3 halves on the y direction and a period 3 along the y and the x direction. They will look different. Or can have a period 2 along one direction, period 4 along the other direction. And we create, by tilting the Raman beams, a system which is have these devil staircases arising both along the x direction and along the y direction. So to conclude, what I want to tell you is that you can find also supersolids in spin-orbit coupled bosons, not only in the continuum, but also in two-dimensional optical lattices. Depending on the parameters, the supersolid phases emerge out of the superfluid phases and away from the multi-insulating phases. They can be isotropic or anisotropic, depending on the direction of the spin-orbit coupling that you apply to the principal axis of the optical lattices, the period 2 along the x, period 3 along the y. And they form a dense set. There's a devil staircase of supersolid phases, which arise due to commensurability of the fundamental period of the supersolid modulation and the underlying period of the optical lattice. And these phases are stabilized by the interactions, where unclap processes are extremely important. So I'll stop here. This is what we see for along the x direction, the full phase diagram. And then this is the case of the situation what we find when you tilt the Raman coupling along the angle theta in the plane, xy plane of the optical lattice, and you can see this cascade of supersolid phases. So I'll stop here, and if you have questions, please do so. That concludes the set of lectures. Thank you.
So, questions? Yes.
So, hi, thank you for the three nice talks. So I have a question. You presented the supersolidity in 3 different systems. Is there any advantage of studying supersolidity in each of them, or would you expect to observe the same properties in general in each of them?
Okay, I would first sort of separate a little bit the experimental situation. Let's say if you have a trap or a continuum or a box system, there is something which is different from the lattice case. However, I would say that in the case of dipolar systems and spin-orbit couplings in the same situation, let's say if you compare dipolar systems and the spin-orbit coupling, many of the phases will be similar, even though the physics is slightly different, but the type of phases will be different. The way you type of phases will be similar. The way you control the existence of these phases is that it's fundamentally different between them, right? Because in the dipolar case, you can control these phases by applying an electric field or a magnetic field or tuning the interactions. Okay, that's good. For the spin-orbit coupling case, unfortunately, the systems in which we have created spin-orbit coupling, let's say the prototype example is rubidium boson systems, you don't have the Feshbach resonances that can tune the interactions. But you do have the spin-orbit coupling and the Rabi frequency that can tune the access to the stripe phases. But if you talk about the stripe phases themselves, the structure that they will have will be very similar on both systems. Okay? But the way you approach and get to them is going to be very different, depending if you have dipolar systems, which you can tune this via either the electric or magnetic fields, or you can tune that by interactions, which you can see that in dysprosing, for instance. Or in the case of spin-orbit coupling systems, like rubidium 87, which you don't have, you cannot tune that by interactions, but you can tune that via the dipolar, via the spin-orbit coupling and the Rabi frequency. But the phases in the continuum and in the lattices will be similar.
Okay, thank you. And if I can, I have another question. I saw in some recent works that they study supersolidity in numerical simulations, but not using the Hubbard model as you mostly showed, but using an extended Gross-Pitaevsky equation with a dipole-dipole interaction and quantum fluctuations. So why using one model or another? Is it better, or in which situations do you think it's
okay
better?
Yeah, so it depends on what your starting point is. You know, some people start from an effective theory already, in which includes, you know, you start from some Gross-Pitaevsky equation, and you add or you can calculate the Li-Huang-Yang corrections to add to those systems. And then you can do some Bogoliubov type analysis on that effective theory and get something similar for the case in dipolar systems in the continuum or box or harmonic potentials. You can also take another approach in which you just write down the Hamiltonian, let's say in first quantization or in second quantization, right? And then you don't write this effective theory and then compute based on the original Hamiltonian, in which you have kinetic energy, local interactions, and dipolar interactions, and then start from there. So I would say that those results have to converge at some point if you use an effective theory or if you use the starting Hamiltonian. The effective theory has an advantage that you can try at least to do something, hopefully, a little bit more analytical, but at the end of the day, that it becomes computationally intensive as well. But they should converge to the same kind of predictions. The question of a method versus the other is that if you start from the original Hamiltonian, I think you're not throwing away certain things which you have to recover by using effective theories. Let's say the Li-Huang-Yang term seems to be important to be included if you're using Gross-Pitaevsky equation alone.
Okay, thank you.
So that's sort of just, but the physics should be connected because this effective theory comes from the original Hamiltonian. So if you use the original Hamiltonian, it should be there.
Good. Do we have time for a final question? If someone, I don't see. So Carlos, would like to thank you again for these 3 talks guiding us through supersolids. Let's all thank Carlos again, please.
All right. Thank you.
Hello? Yep. So, continue our session here. let's finish and let's speak a few words about Professor Kristian Helmerson. For those of you who don't know him, he studied at Massachusetts Institute of Technology, earning his PhD in 1991 under Professor Dave Pritchard. He then joined the NIST at Gaithersburg, Maryland, where he stayed from 1993 to 2009, correct? And then he moved to Monash University in Australia, where he holds a professor position at the School of Physics and Astronomy, and leads a research group studying the physics and application of ultra-cold atomic gases, as well as application of optical techniques to address problems in biophysics and biotechnology. Great, isn't it? A common thread in his research is the use of lasers, and in particular optical force that can be generated by light. Current studies with ultra-cold atomic gases include superfluidity and the presence of disorder and or reduced dimensionality, quantum turbulence, and the physics of two-dimensional electron gases simulated by atoms in optical lattices. So, but that's not all. Current experiments also in biophysics include development of techniques for isolating and studying single biomolecules and the behavior of biomolecules in confined geometries and directed self-assembly of nanoscale objects from biomembranes, which states his versatility as a researcher. So he also contributed with our group since the 1990s. He came a number of times that you cannot count. He worked in almost all my early career papers. He is a very versatile and helpful researcher. So please, Chris.
Okay. Can everybody hear me? Is the microphone working? Yeah, good. Okay. So let me begin by thanking the organizers for the opportunity to come to Brazil again and give this lecture at this school. I'm really enjoying being here. So my lecture today is going to be on quantum turbulence, specifically 2D quantum turbulence, and some of the research in the area at Monash University, which is in Melbourne, Australia, in both theory and experiments on the superfluid gas of atoms. Does that work? Great. Okay, so here's an outline of my talk. The theory work was primarily led by Tapio Simula, who was at Monash at the time when we started, but is now at Swinburne University. It's also in Melbourne. And it was critical to have his theory input to help guide and interpret the experiment. So this is very much a collaborative effort between theory and experiment that I'm going to be describing today. So as I mentioned, this is an outline what I'm going to be talking about. So I'll start by giving a very brief introduction to the concept of turbulence, talking about ideas like energy cascades, energy scaling, and so on. But then I'll move on and talk about turbulence in 2D and how it really differs dramatically from turbulence in 3D. Especially this concept, I'm not sure if I should stand here or there, especially this concept of an inverse energy cascade. And then I want to talk about Onsager's model of 2D turbulence. So Lars Onsager proposed a statistical mechanics model of 2D turbulence. Oh, okay. Statistical mechanics model of 2D turbulence. And so I want to talk about that and the concept of using a point vortex model to explain things. And also, as a result of Onsager's model, he proposed the concept of negative temperature states. So I want to talk a little bit about negative temperature states. And then I'll move on to talk about some of the theory, in fact, simulations of 2D turbulence, both using the Gross-Pitievsky equation and also the point vortex model. And then some things that we discovered in the context of looking at the simulations, something we call evaporative heating, which allows us to get to these negative temperature states in our system. And also I'll talk about Monte Carlo simulations of various vortex configurations and how this allows us to do thermometry when we have a really good method for classifying the vortices in the system. And then I'll move on and talk about the actual experimental work, so strategies for observing these vortex dynamics in 2D turbulence. I'll talk about a quasi-2D homogeneous trap that we developed to study this system. And then I'll talk about how we generate the vortices in the system and how we actually identify the vortices and the configuration of vortices in the system. And finally, I'll talk about the actual experimental results and our measurements of negative temperature distribution of vortices. All right. So I don't have to really convince this audience here that turbulence is a technologically important but very complex phenomenon. Now, the velocity field of classical fluid is described by this equation, the Navier-Stokes equation. But this equation is nonlinear, and turbulence is a highly non-equilibrium phenomena, which makes finding sort of general solutions of this equation in the turbulent regime very, very difficult. Now, Da Vinci was one of the first people to notice that turbulence involves sort of swirling motion of the fluid. And so looking at vortices could be a key to understanding turbulence. Now, turbulence itself involves transfer of energy across many different length scales. And there's a range over which you can get energy to transfer over different length scales, which doesn't involve any dissipation, and that's called the inertial range. And this person here, Louis Fry Richardson, who was sort of an atmospheric physicist, he proposed a mechanism involving vortices, or swirling motion of the fluid, for this transfer of energy. So you imagine that you generate sort of large-scale vorticity in the system, and this large-scale vorticity can break up into smaller vorticity, which can subsequently break up into smaller vorticity, and so on. And so you have a way of transferring energy across all these different length scales until finally you get to a length scale where you can have dissipation, take the energy out of your system. So as Richardson said, big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So I guess in addition to being an atmospheric physicist, he was sort of a poet. So. All right, so this provides sort of a phenomenological description of the development of turbulence, this energy cascade. And often this form of energy cascade is referred to as a Richardson cascade. So another important person in the development of a physical description of turbulence is this man here, Kolmogorov, who was a mathematician. And he provided a statistical mechanics or a statistical description for this energy cascade. So the other one was just sort of a picture of the energy cascade, but Kolmogorov actually provided a statistical description of it. So in Kolmogorov's statistical description, you first assume that you have the excitation of the fluid at some energy scale or some length scale. But that sort of disappears after a while. So you assume that that disappears. And then you assume that as the cascade is going on, that process is homogeneous and isotropic at every step. And based on that, the cascade process looks self-similar, and so you can predict, it begins to have some sort of universal behavior, and you can predict scaling laws. And one of Kolmogorov's famous results from his statistical picture of turbulence is the energy spectrum of turbulence, 3D turbulence in this homogeneous isotropic system. And he predicted that the energy should scale as k to the minus 5/3 power. So in other words, k is the wave vector associated with the turbulence. And so basically you expect the turbulence to scale as the length scale to the 5/3 power, okay? So Kolmogorov's statistical description has, the fact that he could even come up with one, has been a driving force for people to try to develop a more general theoretical description of turbulence. But what about two-dimensional turbulence? So there are many examples in physics where if you reduce the dimensionality of the system, it can lead to quite different results. So for example, we know that if you have a homogeneous 2D system, you can't have a BEC, but you can have superfluidity via the Brzezinski-Koslowitz-Thales mechanism. And in fact, yesterday we heard from Randy Hewlett that if you went to a 1D gas, you can get things like spin charge separation. So changing the dimensionality of the system can lead to results that you wouldn't normally see in a 3D system. And that's certainly the case in turbulence. So in turbulence, you can have, which is essentially two-dimensional flow, you also have some unusual behavior. And this is because in two-dimensional flow, or you often observe the formation of large-scale, long-lived vortices. So you see large vortex structure in two-dimensional flow. And such behavior can be observed in systems ranging from planetary atmospheres. So, the atmosphere is thin compared to its extent, so it's essentially a two-dimensional fluid. And so you often see in atmospheric flow large-scale vortex structures like hurricanes and things like that. And a classic example of this is the giant red spot in Jupiter, so this giant vortex structure in the atmosphere of Jupiter. But you can also observe this phenomena in things like, very shallow streams. The water passes through the rocks and you get some turbulent flow. But if you look downstream, you find that the swirling motion of the fluid is even bigger. People have also observed that sort of behavior in more controlled systems in laboratories, like, for example, in studies of soap films. Here's an example from Rutgers University where they have a soap film, and the soap film is flowing past these little obstacles. And you can see further downstream, you see that large-scale flow developing. Okay. So this is something that you actually observe in two-dimensional turbulence. So I've already mentioned that in three-dimensional turbulence, you can have this energy cascade. So you can have the flow of energy from large length scales to small length scales. But in two-dimensional turbulence, what you have is something called an inverse energy cascade. So you can have the energy flow from small length scales up to big length scales. And so this is what results in this sort of large-scale motion of the fluid. And in fact, in two-dimensional turbulence, you have both the traditional energy flow and this inverse traditional energy cascade and the inverse energy cascade. So you imagine you have some excitation at some length scale here. Some of the energy will actually go through the normal energy cascade to smaller and smaller length scales, but some of the energy will actually follow this inverse energy cascade and go towards larger and larger length scales. So the appearance of these vortices, this large energy, long-lived vortex structure led Onsager to propose a statistical mechanics model of 2D turbulence. In fact, Onsager had a paper called, I think it was called Statistical Hydrodynamics. And in fact, his only paper on statistical hydrodynamics, but it's a very influential paper in 1949. And in that paper, he said, the formation of large isolated vortices is an extremely common yet spectacular phenomenon in unsteady flow. So unsteady flow means turbulent flow. Its ubiquity suggests an explanation on statistical grounds. So Onsager wrote this paper on statistical hydrodynamics to explain two-dimensional, the appearance of this large vortex structure in two-dimensional flow. And Onsager, in the paper, Onsager approximated the fluid, or the vortices, the vorticity in the fluid by point vortices. So he basically said that turbulent flow corresponded to a random arrangement of point-like vortices. So if you have point-like vortices, they can either flow clockwise or anti-clockwise. And if you have a random distribution, he said that that corresponded to turbulent flow. And the reason he did this is because then he could actually do the statistical mechanics, as opposed to a classical fluid where you have vortices of all different sizes, which is much too complicated. So essentially what Onsager used in his analysis is what's called the point vortex model. And so this is the this is the equations of motion for the point vortex model. And it's been around for many years. It's been used to explain two-dimensional motion of charges, for example, by people like Helmholtz. But using this point vortex model, Onsager proposed that at high energies, there would be clustering of vortices. So you initially start with a random distribution which corresponds to turbulence, but as you put more energy into the system, then he expected these vortices, this random arrangement of vortices, to to change, and there would be clustering. So vortices of one sign would be clustered over here, and vortices of the other sign would be clustered over here. And when you have a clustering of vortices, he said this corresponds to large-scale circulations, because all the flow field from each vortice adds up, and you get large-scale circulation around the clusters. And so Onsager said this is what gives rise to this large-scale motion of the fluid based on this point vortex model. He also, in this paper, proposed the concept of negative absolute temperatures. So he said that the clustering of these vortices from the statistical mechanics picture corresponds to negative temperature states. So this is the first mention of negative temperatures, and it was proposed by Onsager in the context of explaining two-dimensional turbulence. Now, because the model involves point-like vortices, it's really only applicable to superfluids. And Onsager knew this. In fact, he said so in his paper. He said it's really only applicable to superfluids. And that's because he pointed out that in a superfluid, you have quantized vortices. And he actually did this in the footnote of the paper. So this is the first mention of quantized vortices in a superfluid ever. And he did it in the footnote in the paper, because I guess to him it was obvious that it should be that way. So because the model is really only applicable with superfluids, it's hard to, people haven't really used Onsager's model to do any sort of quantitative explanation of, or quantitative analysis of two-dimensional turbulence. They often just use it as a sort of a hand-waving or a toy model to explain why you have the giant red spot in Jupiter. But it's possible now to actually do the experiment and do a real quantitative comparison of Onsager's model, or quantitative verification of Onsager's model using a real superfluid. And that brings me to the concept of superfluid turbulence. So in superfluid turbulence, in a superfluid, we have quantized vortices, and we can study the behavior of the quantized vortices as proposed by Onsager. And in fact, when you actually look at the quantized vortices in the system, it's often referred to as quantum turbulence. So superfluid turbulence also refers to wave turbulence in a superfluid. But if you focus on just the behavior of the vortices, then it's often referred to as quantum turbulence. So it's a subset of superfluid turbulence. And in fact, superfluid turbulence can also has an energy cascade mechanism that's very similar to the Richardson cascade, and it was proposed by Feynman. But instead of having sort of just vortices, swirling motion of the fluid that goes to smaller and smaller length scales, Feynman proposed that in a superfluid you have vortex rings. And these vortex rings can have reconnection processes which result in the vortex ring breaking up into smaller and smaller vortex rings. And in this way, you can have energy transfer from large length scales to small length scales, so an energy cascade. But when this happens in a superfluid turbulence, then what eventually ends up, the superfluid ends up eventually having this sort of tangle of vortices. So you often hear in superfluid turbulence people talking about tangles of vortices. It's because of this cascade mechanism for the energy involving the vortex rings breaking up into smaller and smaller vortex rings. All right. So one of the things I said that Onsager proposed in his paper on statistical hydrodynamics is this concept of negative temperature states. And it might sound a little strange, negative temperatures, but it's completely compatible with thermodynamics. So shortly after Onsager proposed negative temperature states, they were actually used by people in the 1950s to explain certain NMR results in certain systems. So that's why you find that a lot of people like Purcell and Ramsey and so on had used negative temperature states back in the 50s. In fact, Ramsey wrote a paper in 1956 explaining the whole idea of negative temperature states, because if you've ever read any of Onsager's papers, they're not always clear. Well, the language is clear in Onsager's paper, but he's not very detailed. He just assumes that everybody understands what he's talking about. So. But Ramsey wrote a really nice paper on negative temperature states. If you're interested in that, I'd encourage you to look at Ramsey's paper. But anyway, the idea of negative temperature states is compatible with thermodynamics. And in order to have negative temperature states, the system has to satisfy certain requirements. So one is it has to be described by a temperature, okay, because you're talking about negative temperatures, so it has to be described by a temperature. There also has to be an upper limit on the energy, so there has to be the system has to have a finite phase space. So there has to be a maximum energy that the system can go to. And finally, the system has to be thermally isolated from non-negative temperature states. So it has to be thermally isolated from positive temperature states. And that's because negative temperature states ultimately correspond to higher energy states. And so if it comes in contact with a positive temperature state, you're just going to have energy flow out of your negative temperature system into the positive temperature system. So you have to isolate it from positive temperature systems. So an easy way to, or one way to understand the concept of negative temperatures can be illustrated if you consider a spin system like they did back in the 1950s. So imagine I have a spin system. I have n spins, spin a half system. Let's say that the spin down corresponds to the lower energy state and spin up is the higher energy state. Initially, I start with everything in the ground state, the lowest energy state, okay? So the energy is at the low point, let's just say 0 here, okay? And you have all the particles in the lowest energy state, so the entropy is 0. Now if you put energy into the system, you can excite some of these spins to the spin up state, all right? And when you do that, as you put energy in, you start increasing the entropy of the system, because you can sort of randomly flip these spins into the higher energy state. Eventually, though, you reach a situation where you have equal population in the excited state and the ground state. So you reach a maximum entropy in the system. And when you try to put more energy into the system, what you end up doing is putting more population in the excited state compared to the ground state. And so the entropy starts decreasing at that point. And if you use the standard definition of entropy in thermodynamics, you can see that in this area, this corresponds to having a negative temperature. So that's why Onsager said that when you end up with, having the swirling motion of the fluid, you've actually put you've come up with an arrangement of vortices, which corresponds to a high energy arrangement of vortices. And so as a result, you have negative temperatures associated with the vortex fluid. Now, negative temperature states have been observed with atoms and optical lattices. There was this experiment in Emmanuel Bloch's group in 2013. Also, more recently, Takahashi has observed negative temperatures of spins and optical lattices. But you can also observe negative temperatures with vortex distributions. And so that's actually what I want to focus on, because it's what Onsager originally proposed in his paper in 1949. So to understand that, the behavior of vortices and negative temperatures, we have this sort of generic picture of a finite 2D Bose gas, okay? So at 0 temperature, or at 0 energy, or lowest energy state of the system for a finite 2D Bose gas is a Bose-Einstein condensate. Now, if you start putting energy in, you start exciting vortex-anti-vortex pairs in the system. So you get vortex-anti-vortex pairs popping up in the system as you put energy into it, okay? And the entropy of the system starts increasing. Eventually, you generate enough of these vortex-anti-vortex pairs that you cross the BKT transition, the superfluid transition, and you destroy the superfluidity. And as a result, all you have is a random distribution of vortices in the system. And so here, when you have a random distribution of vortices, you're at high entropy. But you reach sort of a maximum entropy because for a finite system, you can only put so many vortices into the system. So you reach sort of even though they're randomly distributed, you reach a maximum entropy of the system. But if you try to put more energy, then the system will have to rearrange the distribution of vortices to take up that extra energy. And the way it does it is it takes it up in the flow field. So each vortex has a flow field associated with it. And so if you have a random arrangement, it looks sort of like a turbulent flow field. But if you put more energy in, you can actually take up that energy by having an arrangement of vortices where the vortices of like signs start to cluster. So you get this large-scale circulation of the fluid, and the kinetic energy associated with that flow field is basically taking up the extra energy. But when you do that, this arrangement looks a little more ordered than the random arrangement. So actually, in fact, the entropy is decreasing. And so you're in the negative temperature regime when you start having this sort of large-scale flow in the system. Eventually, you can probably get to the maximum energy where these vortex clusters, in principle, should collapse to two multi-charged vortices of opposite signs. But the basic idea is that as you put energy into this system, if you have a turbulent arrangement of point-like vortices, as you put energy in, they should start clustering. And this cluster is often referred to as an Onsager cluster of vortices for this reason. And this corresponds to being in the negative temperature regime. So in order to identify the feasibility of doing these experiments on the system, we actually started by first looking at the Gross-Pedievsky equation. And so here's a little movie based on that. Let me just see if I can get this running. So in the Gross-Pedievsky simulation, what we did is we put 40 vortices in, 20 that are rotating clockwise, 20 rotating anti-clockwise, and we've labeled them with blue and green, respectively, in the simulation. So the first thing that happens is that with this random arrangement of vortices, is that when a green vortex and a red vortex, anti-vortex come together, they can annihilate. So initially what happens is you get a lot of annihilation processes in the system. This generates sound in the BEC, and so you can see this sort of the background fluctuating there, which is the sound waves. This little white line here is sort of the average distance between vortex and anti-vortices. Oops. Oh, anyway. And let me just run it one more time again. See if we can get this. So you can see the initial annihilation happens quite quickly. You lose vortices and anti-vortices. You can just stop it maybe somewhere around here. But you can see that as a result, you get this sort of behavior where vortices of one sign tend to cluster together and vortices of the other sign tend to cluster together. And it becomes, you get more and more, as the system evolves, the clustering becomes more obvious. But the average dipole of the system is increased because you have basically a dipole between clusters. Also, the annihilation process slows down because now you have this clustering means that the vortices and the anti-vortices tend to want to separate, so you don't have as many annihilations happening. So I gave you this sort of generic picture of a 2D Bose gas and described how you can get this clustering behavior as you put energy into the system. But some of you may have noticed we just did a GPE simulation. And the GPE simulation is basically a closed system. We start with a certain energy configuration of vortices, and we just let the thing evolve. So you might be wondering, how can you actually go from a situation where you have a random distribution of vortices to a situation where they start clustering when you're not actually putting any energy into the system? And our explanation for this is something we call evaporative heating. So when a vortex and an anti-vortex you have a vortex and an anti-vortex pair in the system, and you have a flow field associated with them. And when they're far apart, there's a very large flow field. So you get the flow field of one vortex adding to the flow field of the anti-vortex. And so there's some swirling motion of the fluid associated with that. But when they get closer and closer together, then the flow field of one of the vortex will cancel the flow field of the anti-vortex. In fact, if they're right on top of each other, which would correspond to an annihilation process, the two flow fields cancel. And so, but that's exactly the situation you have when you have annihilation. A vortex and an anti-vortex come together and annihilate. So in other words, every time we have an annihilation process, we're removing pairs of vortices. We're removing vortex-anti-vortex pairs that correspond to a low kinetic energy configuration, so a low flow field configuration. And what's remaining then are the vortices, arrangement of vortices, which correspond to the large-scale motion of the fluid, or a larger fluid flow between the pair of vortices. You can understand this in terms of that spin picture that I mentioned earlier for describing negative temperature states. If I have some distribution of spins, a configuration here, and then I come and remove some of the low energy ones, then of course what you're left with is a higher energy configuration. So that's essentially what's happening in this event, in the vortex anti-vortex annihilation process. I'm removing vortex pairs that are in low energy configuration and leaving those behind with higher energy configuration. So effectively, I'm putting energy into the system, or in other words, the average energy per vortex is increasing as a result of this annihilation process. And just to verify that that's in fact the case, that really what's important here is the dynamics of the vortices and the annihilation. We did a point vortex simulation using the equations of motion for the vortices shown earlier in the point vortex model. So in this simulation, we have 80 vortices, 40 of each sign. And we've artificially put in the situation that if they come within a certain distance of each other, a vortex and an anti-vortex, we remove it from the system. So we've artificially put in annihilation into this point vortex model. And you can see in this system that you observe the similar behavior, that after a while, initially you lose vortices, but after a while, what you're left with are sort of clustering behavior of these point vortices. So you can see after a number of simulations, you see initially a rapid decay of the number of vortices, okay? But then you observe sort of this clustering behavior. The average, the effective dipole moment of the system is increased, but the average energy per vortex is also increased as a result of removing the low energy configuration of vortices. So this is the mechanism that we think is responsible for driving the system from this turbulent state into the cluster state. Now, we've shown that we can certainly, from the simulations, we can certainly calculate what the average dipole moment is. But really, we need something that's a little more quantitative to compare to Onsager's model. In particular, we'd like to know what the temperature of the vortex distribution is. And to do that, we have to classify the vortices in the system. And so we've come up with a variation of some previous vortex classification schemes, where if we have a collection of vortices in the system, some distribution of vortices, then you sort of pick one and you start moving radially outwards. And if you run into one that has an opposite sign, then you say that these two belong to a vortex pair. So you classify this as a vortex pair. And then you go to another vortex, let's say this one here, and you move radially outward. If you encounter a vortex of the same sign, then you say they belong to a cluster. And this way you sort of classify all the vortices in the system as either belonging to pairs or clusters. And whatever's left after you do the classification, you consider them as free vortices. And the reason we do this is that we also looked at Monte Carlo simulations for various equilibrium vortex distributions. And we found that there's a correlation between the fraction of vortices that are pairs or clusters, and the temperature of the system. So at low temperatures, we see that mainly almost all the vortices in the system actually belong to pairs. Very few of them belong to clusters, and there are some free vortices in the system. As you start increasing the energy in the system, then what happens is eventually you get sort of a random distribution of vortices, which we said corresponds to this turbulent state. And in that situation, basically the distribution of vortices are distributed equally between dipoles, clusters, and free vortices. Now, if we put more energy into the system, where we'd expect the vortices to start clustering. In fact, that's what we do, what we observe. And when that happens, you actually find that the vortices here, the fraction of vortices that belong to clusters increases, while the fractions that are correspond to pairs or free vortices decreases. But the key thing here is that there's a monotonic relationship between the fraction that are identified as pairs or clusters and the temperature of the vortex distribution. So this allows us, if we know the distribution of vortices, to uniquely assign a temperature to the vortex distribution. All right. So that's some of the theoretical work and simulations that we did in preparation for doing the experiments. So now I want to talk a little bit about the experiments. So there's been substantial work over the past 50 years in studying superfluid turbulence from the liquid helium community, going back all the way to some early work done by Joe Vinan on looking at mutual friction in liquid helium. And so I don't want to talk any more about liquid helium because there's lots and lots of papers and lots and lots of studies of it. People recently, though, have been looking at superfluid turbulence in ultra-cold atomic gases. In fact, the first experiment was done here in San Carlos in Vanderlei Bañado's group, where they had a cloud and they would shake the cloud rather violently. And what they observed, they had some evidence of a vortex tangle and some sort of non-standard time of flight expansion of the cloud. More recently, people like Zoran Hazibabek's group has been looking at superfluid turbulence, but they've been focusing mainly on wave turbulence. But they've been able to actually observe the energy cascade in wave turbulence in the superfluid. So these experiments are essentially on 3D systems. What about 2D systems? Well, in 2D systems, there's fewer experiments. There's certainly fewer experiments in liquid helium because it's very difficult to access the 2D regime in liquid helium. And that's because if you want to get into the 2D regime for studying in liquid helium, you need to get to a length scale, you need to basically have a thin enough layer where the layer's thin comparable to the vortex core size. And in liquid helium, that's sort of comparable to the surface roughness of any container, so it's very difficult to create a system in liquid helium to study 2D turbulence. On the other hand, it's rather easy for a Bose-Einstein condensate of atomic gas. So really, all you need to do is take your gas and compress it down. You don't even have to compress it all the way into the real true 2D regime. You just have to compress it far enough that you have the vortices are aligned. So when we talk about being in the 2D regime for fluid flow and studying vortex dynamics, we just want the vortices to stay aligned. We don't want them to tilt. And so you only need to get to something like 5 times the healing length or 5 times the vortex core size compression to observe two-dimensional flow of the vortices in the system. So if you want to study two-dimensional turbulence, I would say, looking at working with cold atomic gases is sort of the ideal system right now, especially compared to the liquid helium. So there's been a few experiments, so people realize this, and there's been a few groups trying to look at two-dimensional turbulence, in particular trying to observe the Onsager type vortex clustering, One of the first groups to go in this direction was Brian Anderson's group at University of Arizona. And so he observed that when he had a sort of a turbulent distribution of vortices in his 2D trapped gas, he could observe that it basically generated some sort of persistent current. If you had a plug in the middle, you had sort of a persistent current developing in this system. Yong-Il Shin's group in Korea has also been looking at vortex behavior in 2D, in a two-dimensional gas. And so they've observed studied the annihilation process of the vortices in the system. But neither group has been able to observe these Onsager vortices, which brings me to the experiments at Monash University. So in order to observe this transition to these negative temperatures, you have to, there's a few things you need. First of all, we had to go to what's quasi-2D flat bottom trap. So I call it quasi-2D because it doesn't have to be truly 2D, it just has to be 2D with respect to the movement of the vortices. But it was key to use sort of a flat bottom potential as opposed to a harmonic potential. So the work in these two groups were actually in harmonic potentials, even though the confinement was fairly tight in one dimension, it was still a harmonic potential. And so we actually had to go to a flat bottom potential. And the reason we did this is that simulations by Andrew Groshek, who's a PhD student in Tapio Simula's PhD student, showed that it's much easier to observe the clustering behavior, or you get a larger separation of the clusters when you go to a flat bottom trap compared to harmonic. So he looked at various power law trap walls with power law walls. And so this is the case where R squared, so this would be a harmonic trap, and this one is a fairly sharp wall, R to the 100 type walls. And clearly it was obvious that you could see the clustering much better. So we had to go to a quasi 2D flat bottom trap. And experimentally, we do it by first confining the Bose condensate. So we're working with rubidium-87. We confine it tightly in one dimension in the node of a Hermite-Gauss mode. So we have a hologram that we use to generate this mode of a laser beam, and we can confine the atoms in the node of this mode. And then, so this gives us a tight confinement to create the quasi-2D geometry. And in order to create the flat bottom potential, we basically use a digital micromirror device to create a potential wall like this. And so if we fit the intensity distribution, it looks like about an R to the 12th potential at the wall. So it's a fairly flat bottom trap with fairly steep walls. So the next thing you need once you have the quasi 2D flat bottom trap is you want to generate the turbulence in the system. And the way we generate turbulence is we drag laser beams through the cloud of atoms. So it's been known that if you drag some potential through the superfluid, then in the wake of the superfluid you get vortex-anti-vortex pairs shedding off the edge of this barrier that you're dragging. And we create an array of barriers, again using the digital micromirror device, the same one that's generating the walls. We can generate a grid of barriers, and the intention was to sort of mimic sort of grid flow in studies of turbulence. And we just basically drag these barriers through the superfluid, which you can do because the digital micromirror device is dynamic. We in fact generate two grids and drag them in opposite directions. And the reason we do this is to avoid any sort of net movement of the fluid due to dragging of the barrier or net drift of the fluid. And when you do this, and then later you release the cloud and look at it in time of flight expansion, you see a bunch of vortices in the system. So all these little holes here correspond to all the vortices that we've generated by dragging these grids through the fluid. All right. So now we have a way to generate, we have the flat bottom trap, a way to generate turbulence. next thing we need is a way to detect the flow pattern, okay? And so to do that, you really want to identify the location and also the sign of the vortices. Oops. So here we know where the vortices are, but we can't tell which, whether this vortex here is rotating clockwise or anti-clockwise. And without that knowledge, we don't really know what the net flow field is of all these vortices. So really, we want to identify not only the location, but we want to identify the sign of the circulation. And to do that, we use velocity-selective Bragg scattering. So in velocity-selective Bragg scattering, you have a two-photon process that go from one momentum state to another momentum state. And via this stimulated two-photon Raman process. And this process is sensitive to the Doppler shift. So it's sensitive to the velocity of the cloud. And you can use this to basically map out the velocity distribution. In fact, it was done originally, it was done back in 2006 by Sergio, when he was a postdoc in Chandra Raman's group, used it to look at the flow field associated with a vortex array. We've also used it in the past to look at the flow pattern or the velocity field associated with a single vortex. So we did some work where we generated vortices and BECs by transferring orbital angular momentum of light to the cloud. And then we used a number of techniques to verify that, in fact, this would correspond to a vortex with circulation, various interference measurements, but also we used Bragg scattering, velocity-selective Bragg scattering, to look at the velocity field. So here's a map of the velocity field associated with this vortex. More recently, though, Young-Il Shin's group had used it to identify the circulation and signs in a sort of a random distribution of vortices. So you have a random distribution of vortices, and he used two pairs of beams to do the Bragg scattering. And one pair would be sensitive to velocities in this direction, and the other pair of beams would be sensitive to velocities in that direction. So when you apply both of them at the same time, you kick out some of the cloud with velocity in this direction, and some of the cloud gets kicked out this way with velocity in this direction. And then if you color code these two clouds and superimpose them, by going and knowing the location of these vortices, you can tell, if you go from red to blue, then it corresponds to a vortex rotating one way. And if you go from blue to red, it corresponds to a vortex rotating the other way. Because effectively what you're doing is you're measuring the velocity on each side of the vortex using this technique. So we did this, and you can get this sort of pattern from the experiment. And then what we do is, since we know the location of the vortices, we can actually generate the equivalent flow pattern in a point vortex model. So this is, we put the vortices in a point vortex model and look at the velocity component along the direction of the Bragg scattering beams. We also allow we look at all different configurations, or this is we have the location, but we look at all different arrangement of signs of vortices, and we try to find the one that has the best match to the data. And it turns out that there's really only one that matches to the data. And once you know that, then we essentially know the configuration of vortices in the system. So from that, you can actually tell what the flow pattern is. So we measure a number of vortex distributions under various conditions. And we've measured vortex distributions in the dipole regime, in sort of the random regime, and also in the cluster regime using this technique. And as I mentioned, one thing we wanted to do was actually identify the temperature of these distributions. So once we have the distribution of vortices, we know their sign and their location. then we can classify them according to our scheme of whether they belong to pairs, clusters, or free vortices. And then we can basically, based on the fraction that are clusters and dipole pairs, we can put them on our thermometry curve. And once we put them, find the location where they best fit the thermometry curve, then you can essentially read off the temperature. So we do this for a bunch of different changing parameters of the system. For example, changing the grid size or changing the hold time of the vortex in the system. And so we can actually create distribution of vortices going from low positive temperatures all the way into negative temperatures using this technique. In addition, we can extract out other information. For example, we can identify not only the temperature, but we can identify the correlations of the vortex, whether the nearest one has the same sign or opposite sign. We can identify the dipole moment of the system, and also the energy per vortex. So here's an example where we looked at it as a function of different grid sizes. So when you have a fine grid, then you generate sort of a distribution of vortices that are more random, because every one of these grids will generate a vortex-anti-vortex pair. So you have a vortex-anti-vortex close to each other. As a result, you expect to see mainly pairs in the system, and that's in fact what we observe. As you go to larger and larger grid size, then the generation of vortices and anti-vortices are more well separated, and you absorb more clustering behavior. So, you start with for small grid size, you're generating positive temperature vortex distribution, and for large grid size, you're generating negative temperature distributions. And since we know what the vortex, once we know the configuration of vortices in our system, from the point vortex models, we can actually generate, or we can actually, we can generate these, the energy spectrum associated with that distribution. And so here are the energy distributions for these different configurations of grids. And so unfortunately, our initial range is too small to really fit to find out whether it obeys a Kolmogorov spectrum or some other spectrum. But here's sort of the lines just to indicate kind of where it should be. But the key thing here is what we observe is that when you get into the clustering regime, you see a buildup of energy at large length scales, so small k vectors. And that corresponds, that's what you'd expect when you have clustering behavior. Also, we have some evidence of this evaporative heating mechanism that we propose to explain why we can go from a random distribution to a clustered, why the system evolves from a random distribution to a clustered distribution. So if we pick a 6 micron spacing grid size, then initially when we sweep it through, we generate basically equal fractions of clusters, dipoles, and free vortices in the system. So this would correspond to the random distribution or the turbulent distribution of vortices. But then as the system evolves over time, so as we hold the sample, the trapped atoms with the vortices, then you get vortex and anti-vortex annihilation happening. And over time, what happens is that the fraction that are in clusters increases and the fraction that are in free vortices decreases. And as a result, the temperature initially, which is starts at an infinite temperature, so beta is 1 over the temperature. It starts at an infinite temperature, but then it evolves towards a negative temperature when you get to the clustering regime. And similarly, what you find over time is you find that in the energy spectrum is you find a buildup of the energy at small length scales, at large length scales, small k vector over time. All right, so basically what we've done is we've been able to verify Onsager's model of 2D turbulence. We've done a quantitative verification of Onsager's model of 2D turbulence. We can see the formation of these negative temperature vortex cluster states. And we can also see the system evolving from positive to negative temperatures And so we think this system is going to be good for studying other types of non-equilibrium dynamics. For example, we can look at more long-time behavior and study like thermal fixed points in this non-equilibrium situation. I also want to point out that in addition to while we were doing our experiments, there was a group at University of Queensland led by Tyler Neely, who was also doing similar type experiments in their 2D BEC. And they could observe also clustering of the vortices directly. But they didn't have the ability to identify the sign of the circulation. So even though they could generate these highly clustered states, they couldn't really see the transition from turbulent to clustered in their system. Okay, so I just want to acknowledge the people that actually worked on the experiment. So there's Tapio, was the theorist on it. We also had input from Matt Davis and David Paganin. But like most successful experiments, really the work is done by some excellent students. And on the theory side, it's Andrew Groshek, who this is his PhD thesis work, did quite a bit of work on understanding the system. And on the experimental side, it was Sean Johnston, his PhD work. All right, so thank you for your attention.
Okay, so we can take questions. Sure, please. Not you.
Well, Chris, thank you. Very nice experiment and demonstration. I have a first one comment. In the paper of Norman Ramsey on the negative temperature, it's, you know, I could, it's relative, right? I could say that this part is positive and that is negative, depending on the spin. We define the positive temperature because that's the way we define the variation of the entropy, right?
Yeah.
Because I could have more spin down or more spin up. So physically it does not make a difference having positive or negative in that sense, right?
Yeah, well, it's just relative to what you call the ground state of the system.
Just a curiosity. Yeah. Now, a question is, you show that the simulation, when you have a flat potential, is easier to clusterize.
Yeah.
It's easy to separate. And why is that? I mean, it's because the density profile, when you have your fluid, somehow influence the interaction between the vortices and anti-vortices, or?
Yeah, essentially, the vortices tend to want to, well, first of all, if it's flat, it's just easier for them to spread out, right? It just, translationally, they can move anywhere. But I think what's happening is when you have the harmonic trap, they just tend to want to, the vortices just tend to want to go towards the center.
Yeah.
Because what you're doing is you're putting more energy into the system, and that would correspond to having larger flow, right? So there's two ways. You can either have the flow go faster, or you can move more fluid. So when they go towards the center, they're moving more fluid.
So basically what you're saying is the presence of an inverse cascade, which is making the cluster, depends how you confine the two-dimensional fluid.
Yeah, well,
so that's true only for a uniform kind of 2D?
No, you can, it should still happen. It's just easier to see.
But I may have a confinement that will never happen.
Oh,
it'll be hard.
If it's really tightly confined, it might be difficult, but in principle, the cluster should still happen.
Even being a 2D.
Yeah, the problem, experimentally though, it's easier when you have a flat bottom trap because as you start bringing even if they're clustering, if you bring the clusters close together, they're going to annihilate.
No, I understand. I mean, the simulation is quite clear. The thing is, we have an extra term, that we have an extra fact that we don't need only 2D, we need 2D in very special conditions, maybe, or in a class of conditions.
No, I think in principle you could if we could generate more vortices initially, then I think you could probably observe it in the harmonic track.
Okay. Now, when you have the cascade in 2D, that's an evidence of the turbulence.
Yeah, yeah.
I mean, that's the main evidence of turbulence.
Yeah.
But after they clusterize, after they separate, and then I stop the cascade.
Yeah, so that's
Yeah, but that's coincide with your seeing the. I could not see very evident the slope of the energy profile there, but when you show the spectrum.
Do you want this one or the other one?
Well, I
This
think
doesn't
it doesn't matter, right?
Okay.
This one is fine.
Yeah.
Yeah, I did not see on the data a clear slope between places that I would expect it, which is between, like between the, there is a range there.
Yeah, so that's what I said. Our inertial range is quite small, so it's really hard to see a change of the slope. So this out here looks like k to the minus 3, which is the energy spectrum for a vortex. And then somewhere in here you have the slope which corresponds to the cascade. And whether it's Kolmogorov-like or whether it's k to the minus 1, we really can't fit it because it's the range, inertial range is just too small in our system.
But in time, I could see the decay of the 2D turbulence, whatever it clusterized, right?
Yeah.
If I want. Okay.
Also, it's harder to see the cascade in the system because we're not continually driving it. So I think if you could continually put in vortices and continually put energy in, and energy's dissipating somewhere else, then you should be able to see the cascade better.
You should see clear, right?
Yeah.
Thank you.
Thank you, Vanderlei. Anybody else? Please come over. Yeah, Professor Lauro first, and then you.
Thanks. Very nice talking with you. I just want to know one thing, because you showed something in the beginning about the Gross-Bitaevsky simulation. In this case, I didn't catch what the interaction that is being used to this simulation. Should be time dependent.
Oh, it's just a mean field type interaction. Yeah.
Okay.
Yeah.
To create this turbulence and after the...
Yeah, so it just depends on the density of the gas. Yeah, mean field.
Yeah.
Thank you. Next, please.
So thank you for the talk. And as I understood, you need to identify very complicated patterns. And is there any effort or perspective to use artificial neural networks to support the analysis of the data, since you can provide a large amount of training data using numerical simulations? And is there any perspective to use ANNs?
Yeah, so there's, we can identify these vortices and assign their signs. Here we have 14 vortices, but if we get to much more complicated situations, it becomes much more difficult. And so there's, Tapio Simula has a paper on the archive now where he's done an analysis using machine learning to identify this, so that, which might be able to extend this into more complicated distributions. So yeah, it's possible. At least he thinks it's possible to use machine learning. So.
Thank you. Anybody else? Please come over.
Thank you for the talk. I was wondering if, because you were showing that the experimentally it's a big challenge to, for example, when you go from 3D to 2D, right?
So, for example, if you can you study this quantum turbulence using paraxial fluids of light? Because in that case, they are pure 2D systems. For instance, thermal vapors.
So you want to use light to?
Yeah, yes.
Um,
Because the dynamics essentially is described by a nonlinear Schrodinger equation.
right. So it's light going through some nonlinear medium or something?
Yes.
Yeah. In principle, yeah, you should be able to do that. Another system where you might be able to observe this is maybe a 2D electron gas or something. So.
Okay. And I didn't hear anything about finite temperature effects. So in these studies, have you made any considerations on this?
Yeah, so certainly in the GPE simulation, we don't have, we just did zero temperature GPE. So. And it seems to agree quite somewhat with what we observed, so we didn't really bother to look at finite temperature effects. I know Andrew was thinking of looking at finite temperature effects, but I don't think he ever got around to it. So not really sure, I mean, what that's going to do to the vortex. The other thing is, in the point vortex model, you don't have any sound, but in the real system, you do have sound in the vortex, anti-vortex annihilate. We did look at the time scale for, because ultimately, if you let the system evolve long enough, then everything's going to go back to the positive temperature. But for over some time, the time scale of the simulations that I showed in the experiments, there seems to be a separation between you can consider the vortices as a fluid separate from the sound, or the wave behavior. But eventually they're going to couple together, and then you're going to lose the negative temperatures.
Okay, thank you.
Thank you. Any other question? Comment? Okay, Chris, I do have a few questions, a couple of questions. Just checking out, how did you find out about this 5 helium length or characteristic length to reach the 2D regime from real 3D?
Yeah, so part of it's observation. I think it's in the literature somewhere. But also, really what's key is you want to look at when the first Kelvin mode shows up. So, yeah. So, there's the vortex, once it gets to a certain length, can support a Kelvin mode. And so you just want to stay just under that.
Would you say that this is a rather general assumption or take to run any 2D system in ultra-cold atoms and things like that? Or?
Yeah, I suppose if you're looking at vortex behavior, 2D vortex behavior.
The other one is just simple. I just want to hear your thoughts about the finite size of the trap, and it's like like a coral, you kind of limit the vortex motion in a wire. And do you think that might affect what you're seeing?
Yeah, so that's essentially why we have such a small inertial range. If we had a really big system, then we would have a much larger inertial range, and it would be easier to identify the transition, to identify the energy, the scaling for the energy cascades. So yeah, we would be happy to have a bigger system.
So I have to complement what really prevents you from doing that. I guess even for putting energy into the system would be easier too, so you could keep on going.
Yeah, so we're thinking of schemes. We've been thinking a little about how to actually come up with a scheme where we actually keep pumping energy into the system. So it may be possible to have two coupled, you have your 2D flat system, and then you have that's coupled to some sort of vortex generating system, and you keep sending vortices into the system or so on. But we haven't really come up with a really great scheme for doing that. So.
Okay. I'm happy. Anybody else? So if you don't have any more questions, let's thank Chris again and let's finish. Thanks for the great talk.